Okay, so let's have a look at some simple harmonic motion. It's pretty cool. No matter how far the pendulum swings or how big the amplitude is, the time period always remains constant. And this is one of the things that allowed physicists to clearly define time. It also means that you can hypnotize people and tell them to subscribe. So we've got simple harmonic motion is a really kind of interesting type of motion. If you have a pendulum and you set it to oscillating, so you've got a fixed point on the ceiling here, and you give this thing a shove up to here, for instance, it will start to rock back and forth, back and forth. And as it does this, if it's in air, it's going to slow down and the oscillation is going to get smaller and smaller and smaller. But the interesting thing is that the time period for one oscillation will remain constant. Okay. In fact, this is one of the definitions of, or one of the defining features of simple harmonic motion, is that regardless of the amplitude, the time period for the oscillations stay the same. Now, in order to understand this and its importance as well, essentially what we've been given by this is a method of measuring time. So it's really important to physics to understand what's going on with simple harmonic motion. So let's look at a simple example. I think a pendulum is quite tricky, but a spring is a bit simpler. So if we imagine you're looking down on a table, okay, so we're looking from above down on a table. Here's the table, okay, and let's say we have a spring lying flat on that table. Let's put a trolley mass on wheels. So this is like, it's got little wheels underneath here and here, so it can roll up and down. And we've got another spring here that, let's say it's an identical spring, just for, and we fix the springs so they can't move. Okay, the springs are stuck here. All right. Now, the mass is going to sit happily where it is right now. And we'll call this position its equilibrium position. Now, if you wanted to displace this mass to a new position, say to here, or to here, right, or even to here, or to here, okay, in order to do that, right, initially you'd need a small force, because basically springs follow Hooke's law. Okay, so a quick reminder of Hooke's law. You have a spring, so this is just a quick reminder of Hooke's law. Hooke's law, apostrophe S, because I'm clever. Hooke's law is that the force is proportional to the extension. Okay, so basically you get a straight line. Stiffer springs will give you a steeper line. Less stiff springs will give you a less steep line. And Hooke's law states in algebraic terms, it is F is equal to Kx is what you usually are told, but actually it's minus Kx because the force is in the opposite direction to the extension. So if you have a spring and you go from its original length like this to a new length and you stretch it, it's got longer by this much, that's the extension, but the force, the restoring force the spring is providing is in the opposite direction to that displacement, so that's why there was a minus sign there. So that's Hooke's law, and that's what I was talking about here when I was saying that that force there is going to get larger and larger and larger in order to pull it up. So the restoring force actually of the springs are going to be trying harder and harder and harder to pull the block back in each direction as well. So similarly as it would go up, it would be being pulled back to the middle. When it's being displaced downwards, it would also be pulling itself with greater and greater force. Kind of got them in anti-symmetrical here, but the force will get larger and larger as you move it away from its equilibrium position. So what's interesting about this? Well, before we go into the sort of deeper maths about it, another definition that's or defining feature of simple harmonic motion is that the acceleration is always directed towards the equilibrium position. So acceleration is always going to be this way or this way, and it is proportional in magnitude but opposite in direction to the displacement. So displacement would be measured in this direction, x. So let's just say this is our measure of displacement, right? This would be where we put 0 on a graph. Okay, that would be 0 on our graph, and its displacement is going to be the symbol x, right? And this would be our maximum displacement and our maximum negative displacement, right? And yeah, the acceleration is going to be largest at maximum displacement. But if you set this thing to oscillating backwards and forwards, let's say we could attach a pen to it. Okay, so I get a pen. Here's a pen. Rubber on the end. Okay, and I tilted it up and I put it so it was pointing down on the paper there, and I taped it on, right? And I set this thing to oscillating. If I was to draw a sheet of paper underneath this thing, right, you would see a nice curve like this being produced depending on how fast I pulled that paper out, and it looks just like a sine curve. Now, cut to the chase, it actually is a sine curve, okay? But at the moment we don't have any proof of that or any reason to fully believe that, but you'll see later on that there's only one way of determining this, and that's through a little bit of guesswork, which can then be later confirmed properly mathematically. So let's think about what we can see here, okay? So if this is a displacement time graph, then the gradient of this displacement time graph would be, well, what's displacement divided by time? Well, velocity is displacement divided by time, right? So if I was to think about what that would look like down here, I'm just going to make this a bit shorter. Okay, so let's just move this up a bit. So, and let's pretend this table kind of went on a bit further. So let's just think about what that might look like. Okay, how is the gradient of this graph going to look down here? This is a displacement time graph. The one above it is displacement time. So let's write it on here. Displacement. And this is time. Okay, and this time I'm going to do a velocity time graph. Okay, so velocity time graph. Okay, now right here, right here, the gradient is maximum and positive. So I would expect then, because maximum gradient would be maximum positive velocity, here we would have 0 gradient, which would mean 0 velocity, so get it lined up again. Okay, here we've got a high gradient, but it's negative, so this would be maximum negative velocity. Again, drawing a line straight down will help me to sort of pin where that is. Right, so we've gone from high velocity, no velocity, high velocity but in the opposite direction. Okay, another spot where you've got 0 velocity, because 0 gradient, this has 0 steepness, so this would be 0 velocity. And if I sort of sketch on what I can see so far, right, I might even put some curves into it. Right, I'll keep going. So what have I got here? Maximum positive gradient, a very steep gradient going up, so it's positive. So again, draw the line down. Okay, and again a 0 gradient, so from this point down would be 0 velocity. Again, maximum negative velocity. Maximum negative velocity, so just carry on finishing this curve off. Okay, and again here is where there's a 0 gradient. The 0 gradient right here, right, so that would be back to 0 here. So I've gone from a displacement time graph to a velocity time graph. Okay, and you can see it's kind of like they've shifted out of phase a little bit. Now this is all going to help us understand where the equations come from and how they all fit in. In fact, this method of just picking points off this graph and then picking points off the displacement time graph and using them to understand or to sketch out the velocity time graph is really useful. It comes up in exams a lot. Right, so now we're going to go from the velocity time graph to the acceleration time graph. So again, directly beneath this, I want to sketch how acceleration is going to change. Acceleration, I can't spell acceleration because I'm really dumb when it comes to spelling. Okay, so again, this is time, this is time. So acceleration is change in velocity over time, right? So that's the gradient of a velocity time graph. So if at this point the gradient is 0, that means you have got 0 acceleration here. Okay? If at this point you have got maximum negative gradient, that means down here we'd have maximum negative acceleration. If at this point, again, let's just go through it, we've got no gradient, so again this is going to be down here. Here we have maximum positive gradient, which means that we've got a maximum positive acceleration. Here we have 0 gradient, so that means on the line. Maximum negative gradient, which means negative acceleration. 0 gradient, which means no acceleration. Maximum positive gradient, which means positive acceleration. Maximum positive acceleration. Again, I'm going to go through and just sketch on the curve. Okay, so now we can see, right, that defining feature again of simple harmonic motion. We can see that when you've got maximum displacement, the acceleration is in the opposite direction. Okay, we can see that at 0 displacement in the middle, you're going to have maximum velocity. Maximum velocity could be positive or negative depending on which way the spring is moving, whether it's moving up or down. We see a lot of the features of simple harmonic motion as we would already want to start to understand them. Right.